Okay, so here, this is the original challenge. So using transformer models to develop search engine for datasets, charts, and documentation. Develop a natural language search engine to improve the discoverability of ECMWF datasets, graphical products, and documentation using natural language. So we, okay, this is just the agenda that I will follow. So I will present first the deliverables that we have, then the development strategy that we will, I will try to explain through the example that we will see on the deliverables. And then we have some comments and outlook on the project itself, plus question and answer. So, great introduction. So, exactly. So we kind of, the goal of our project in the end was, despite the long title, was to create a chatbot that will allow a broad audience of people, so not just technical people, developers, but general audience to access ECMWF resources in a conversational way, so using natural language. This with the purpose of increase the discoverability and accessibility of the data. So our goal was to create something that was easy to access in conversational style, and that unify also the access to all the different knowledge base and APIs and data that ECMWF has on its servers. So let's give a look at then what's the starting point. So we took then Confluence knowledge base, which is hosted publicly from ECMWF, all the web content which is under ECMWF.int. Then there's some GitHub repositories that we took into consideration, plus the data API and charts API, which are hosted at ECMWF. So these are so quite a lot and diversified unstructured data. Just to have a brief example how the data may look like. So a Confluence page is something like this. It has a content which contains text and images and eventually links. The charts API is an open API, is developed with an open API standard. So one can find all the details on how to access API actually through a JSON format, which is quite useful for us for the project, and we will see why later. Then we have the Mectogram API, which with which one can access directly Mectograms, and this is, let's say this is just a subset of all the charts API that we have. But so we took this as a nice one to start with, because you can just get a forecast out of that. Then we have the Climate Data Store API, which is huge, has hundreds of parameters and different way of calling them, and can be used through different APIs. And then the web content, which is diversified and is mostly unstructured text. Plus GitHub repository, in which we loaded also, we can access basically all the files that one can find under GitHub. So here we took just a ECMWF API client, and we have EC codes and many others. So then we have, as said, on our GitHub repository hosted on for Earth, we have two branches. One using ChatGPT as a large language model that employs the OpenAI API key, which requires subscription. And then we also played with the open source model. In particular, we have a branch that allows to use very different open source large language models, which are cloud hosted, but with a API which is free, so no pay subscription needed. So we then deploy the software through Docker containers, such that people can actually also try and test the application on a normal level. So we don't need to host actually any GPU or server to run all of this. So let's start from the deliverables. So from what actually this dashboard produced. So our dashboard is built with Gradio, which is a nice package for building chatbots. And here we ask, for example, so the one in blue is our user input, and the answer is from the language model. So we ask a metagram for Venice, and the chatbot replies with an image, which is exactly the one that we wanted. So for the date, so we didn't also not specify any date because it's kind of standard. and the standard will be to produce a metro with a 10 days forecast out of today date. And this will grab from the Metrogram API that we have seen. Another demo is downloading some data. Here we were able to embed the CDS API, the reanalysis data sets, so at single level pressure. And here we ask a very broad question, which is download the data for the Hurricane Katrina from the CDS API. And the chatbot allows also for interaction and ask, so whatever data you want for the Hurricane Katrina, are you interested in temperature, precipitation, wind speed, or another type of data? We answer with precipitation, and the chatbot then operates, so requests the data to the API, and then returns the JSON required to make the request. And I let you see that, for example, we ask for precipitation, and the variable in there, we ask for precipitation, the chatbot is able to interpret that as a proper parameter which exists in the data set. And then, so on top of this, we were able to actually, so the chatbot will autonomously download the data. We were able to add on top a simple plotting routine, which extracts from the grid the data and throws that on a map. So this is the result of our query, no? So this was from Hurricane Katrina, and we were able to generate a map from the grid that show actually so with a time slider that allows to see the evolution over time. So then the other tool that we have at the disposal of this chatbot is the Charts API. Also here, we want to also show how the chatbot is interactive, no? In the sense that we may also introduce non-technical, so use non-technical language also incomplete. So we ask, for example, a chart of rain in Asia, no? And the AI responds, could you please specify the time for which you want the chart of rain in Asia? And here I probably misread the question, and I say the whole Asia. And he answered, I understand you want the chart of the whole Asia, however, you need the specific time. In 3 days from now at 16, and he downloads the map. Probably here, so you see is the whole world map, but depending on the query, of course, there are different regions in the Charts API, and probably the one that were best fitting the requests were the whole world. So this is the last tool that we have in our chatbot, and is the knowledge base and documentation. Here we can ask so general user support questions. So show me an example how to retrieve data from the CDS API, and the chatbot will then browse all the documents that are at its disposal, and then will answer, eventually show up a snippet if applicable. And here below we can see that we added the sources that were used to build up this answer. No? So last, then we also added on the dashboard the possibility to give user feedback, which of course is important to actually gather data from the users and understand how to improve certain answers. So this was an overview of all the results that we have with the large language model. And now I will try to explain the two strategies, development strategies that we used for building up this type of products, which seems to be interesting and doing many different things. And we'll use this example to explain so what's happening underneath, no? So first of all, large language models works through prompt engineering. So we supply a certain task to the large language model, which is still a natural language model, which takes as input text and outputs eventually just the next word in the sentence, no? And but are instructed in a certain way that allows to to use different tools. Here, for example, we tell so as a whole, we tell to the large language model that it has at its disposal different tools that certain knowledge base code and then a small description that let the model understands what is the usage for this tool. And then we have other, and then we also need to specify, if applicable, how to call a certain tool. Then here we show that the parameter going needs to specify the latitude, longitude, the station name, eventually for the chart, the valid time, and for the CDS API, and many other different values, no? And then we ask here, so at the end of the prompt, so the way he should format the answer such that we can then further elaborate on the response. So one part, for example, the part of the knowledge base and documentation is based on a concept which is called retrieval augmented generation. So it's a text generation approach that for which there's some data storage in which the text data are stored, and we retrieve the data from there. And there's a generation part which uses the retrieved documents to build up new content that makes sense with what was that has coincidence with what was taken from the retrieval phase. So for this, we employ vector databases in which we can store actually numerical representation of images, documents, and audio, and we can query them easily in order to retrieve always, eventually also at a scale with hundreds of thousands of millions of documents in a fast way, so a match for a given query. So we have some models, some transformer models, some embedding model that translate the image, the documents, audio into vector representation, embeddings, which are numerical representation of certain space. Then the user asks for a query that gets embedded as well in a vector representation. Then there's some algorithm that search for matching results between the two. So with this attempt, then we feed so for example, in the example that we have shown, no, we had, so these were the documents retrieved, no? A README with how to use the CDS API, which is coming from the GitHub repository. Retrieve.py file that seemingly was, the content of this file was actually making a CDS API request. If you remember in the example I showed, we were asking how to make a CDS API request for data. We have another file from the test directory with the repository. And then we have also another README that explains how to use that through Docker. We feed everything. So whenever the model has understood how to, that he needs to use the knowledge base tool, no? Then we will submit to it another prompt, and we tell him, so use the following piece of context that are attached here below to answer to the question at hand. So we always add on top, if you don't know the answer, just say that you don't know. Don't try to make up an answer, because you know one of the biggest problems with this type of model are hallucinations. And based on this, then the model generates a new answer. That is the one that we have seen on the example before. Now, to explain the other, so as I said, this was the knowledge base and documentation part. For the other tools, the metagram, the charts, and the CDS API download, the approach for that is React, which stands for Reasoning Act. So these large language models like ChatGPT, which is the one that we have used here, can actually interact with itself, given enough tools for doing this. So, and this is the best way of letting to integrate existing API. For example, as said, we have APIs in Open API standard, and that's the best way to have that, or the CDS API as well, or the metric, And this is actually, I think, the cool part of this type of algorithm, that it can handle these generic queries and integrating with existing tools. So as we have seen, we give it a query. The LLM understand which tool, so understand the inputs. So reason with itself, trying to understand which tool it needs to use, then eventually asks when it has found what to use, and then generates a response based on the response, for example, of the API. So what's the weather like today? That will be translated into something like this. Understand that it needs a weather forecast for Venice. search the tool, the API that has that amongst the tools that we have shown at the beginning, the first prompt, and then parse the response to the user. So these actually are the example directly from the query that we asked before regarding the Hurricane Katrina, no? And these, as before also, so in blue there's the user, and the other is the internal flow of the large language model. So here, so this is not shown to the user, but actually that's what happened underneath. So here the ChatGPT in this respect says the user wants to download data for Katrina from the CTS API. Hurricane Katrina occurred in August 2005, so he probably already knows that because it's a famous event and probably was trained on some data that contains that. He knows the region where that is happening. So, and then he says, I will need to use the CDS API tool to retrieve this data. That recall was one of the tools that we supplied. So the exact parameter will depend on specific data the user wants. I should ask the user to specify the type of data they want. And indeed, we have seen that he asked us what type of data we want. We answered precipitation. So this ChatGPT is implemented with some memory for the conversation. So he actually remembers the first question. He now note down that we want precipitation, and then say, okay, now I know what I need exactly to do. As we told him to use a certain signature for the function for the request, so he knows that he needs to convert that in latitude and longitude, and that's actually a very good thing that ChatGPT does. So they can basically translate a geographical area into latitude and longitude. And then it's applied the year and date as we suggested to him. And the result is what we have seen. So now I'm going towards the end, and I want to share some comments and outlook on this project. So we employed LangChain as a prototyping framework, which is a very nice framework which tries to integrate many different vector database algorithms, strategies for building up large language models tools. So it has been so also once it's deployed, it has been relatively easy, to integrate very different things and build the dashboard as you have seen with all the different tools. So as I said, ECMWF has tons of resources, and some of them are indeed difficult to reach. And but the LLM has this ability, if so supplied with the proper data, to understand this interconnection and also retrieve to the user. So what we are seeing is so having structured APIs is extremely useful because then it's easier, Well structured means open API standards or XML. So structured data that is easy to parse and fit to an algorithm and also to organize. Everything that has annotation labels, also in Confluence, for example, there's the labels tags that are helpful to trace back the documents to have kind of keyword searches. So this project was not just we throw all the data to ChatGPT and wait for an answer. That's kind of something that we tried at the beginning, especially. So, so what I want to stress out is that still the solution developed is a prototype, and there's many things that need to be fixed. So, and even though it looks like it can do a lot already, there's many different things that need to be processed. So, which is proprietary software. So one needs to pay for that. And in general, for example, we had problems during the development because at the beginning we could not freeze the ChatGPT version. And so over time we had different responses. When we changed it from 3.5 to 4, we actually experienced some queries were not responding anymore as before or not responding at all. Then still, so we uploaded the vector database in June with the Confluence GitHub documents, but also here we need to establish a process on how to update, because when the data are in the vector database, then they are frozen and basically they do not reflect anymore updates on the content, whereas in GitHub, in the Confluence, and the web-based, all the information are, are continuously changing. And then we need, of course, to monitor model responses because there's so this hallucination are happening. And also we have problems, for example, with formatting answer. So sometimes I will just format the answer in a wrong way that is not processable from the dashboard. So probably, having an open source local model, which is trained and eventually frozen in its state, in its weight, would remove part of the dependency from ChatGPT itself. We tried Llama 2, which is available, as said, in a branch on our repository. It's very so it's yielding very good results. It's fully open source, can run on also on a laptop for certain degrees. And then, so there's already, for example, on GitHub, an awesome link for LLM Ops, which is kind of operation with the LLM, which is, how to actually bring to production this type of model. And now, in the next slide, I will show how complicated that can be. And finally, we stress out that it will be extremely important to do a crowd experiment in which we give the dashboard to many different users at ECMWF and now to gather feedback and to understand what needs to be modified, what can be improved, and to monitor especially the response of the model. So here, as a last slide, I've found this on a blog post and I found it interesting because it looks like it's all done by ChatGPT, but actually there's still a lot of job for developers because there's many, this type of application comes with many different models in it. So first of all, the embedding models that translate from unstructured data to structured one, so to embeddings. Then there's, for example, we have seen that we have supplied prompts without any type of examples, but actually we could also create agents with a large language model that for which in the prompts there was also example that, for example, how to call a certain API. This example needs to be maintained over time. Then the API plugins and whatever that externally that is integrated and changed needs to be reflected. So there needs to be some sort of integration. Then there's caching, validation, logging, and average. So it looks like everything works very smoothly with ChatGPT, but actually for bringing this to production, it's a whole job, right? So with this, I am done, and I'm thank you again. So Athena and Esperanza for organizing Go for Earth, the mentors, and Giacomo. And thank you very much.